Hello everyone. Hello everyone. Welcome back again. The day 7 of Cbc class, Course Beyond the Curriculum. Once again, I'm repeating that our course title is Advanced Linear Algebra from Eigen Theory to Modern Statistical Learning. And as of now, module 1 to 4, we completed that. And right now, we are there in Advanced Eigen Theory and the applications in engineering. So the last topic we kept that because which is interlinked with that advanced eigen theory. So the algebraic geometry, multiplicity, and diagonalization of matrices also. Now we can see that. After that, we'll go with that this advanced eigen theory and applications in engineering. Okay. So this after that we'll come back to that. Okay. Next. So what is algebraic and geometric multiplicity? So where we are using that these two terms. So we are using these two terms in with respect to the eigenvalues, right? Now let me come to that here. Suppose let capital A is a matrix, B and n by n square matrix. That means nothing but square matrix. We learn how to compute the eigenvalues and eigenvectors of A. So theoretically I'm explaining, but you very well about that practical. That means a problem wise because you already completed that in a first year and sem 1, right, Nana? So first, the compute the characteristic polynomial det of A minus lambda I, or here I kept that lambda ID, okay, and find its roots, they are eigenvalues. Yes, yeah, det of A minus lambda I we are going to take, and those we are going to get the eigenvalues. If the space will be there and we are going to compute with respect to the vectors, we are going to get that the eigenvectors, right? And let capital A, again the same, I'm not going to repeat that. So when you compute that eigenvalues and then eigenvectors, after that we learn that it is particularly nice and when A has eigenbase, because then we can diagonalize the A. That's the main thing, okay? Then an eigenbasis is a base of eigenvectors. So theoretically, I'm telling about here. Now we can see that how we can carry about this algorithm, how it will be coming out. So I have taken that the simple examples because you can, connect with that, right? The simplest case, the characteristics of has n distinct roots. So say different eigenvalues. Then this is the matrix we have taken, and that we are going to find out with that, okay? And then we got that the n distinct eigenvalues roots means here lambda 1 equals to 2, we got that this is the eigenvector, and lambda 2 is equals to 3, and we got that these are all the nothing but these are all the eigenvalues, and these are all the eigenvectors, okay? So then we can form that if we have a vectors, obviously we are going to form that the basis, right? So when we are going to get that, if lambda values are distinct, different roots, the characteristic column will not have that the roots. So in this case, we don't get that no eigenvalues here. So at that time, at least not real ones, we can talk about the complex numbers in the next lecture. Next, the simplistic, sorry. Next, the characteristics as have repeated roots. See, first case you have seen that n distinct roots. Second case is no eigenvalues. That means no, nothing will be there. And then now, somewhere I'm missing. Okay. Yeah. Now repeated roots. This is the third case. Repeated roots. So say I have taken that this example or whatever that in this, right? So if you take that, you are going to get that the eigenvalues span and all I'm not telling about here, because our concentration algebraic multiplicity and geometric multiplicity lambda values. So A and B have the same characteristic polynomial. So obviously you'll get that the thing. But A has eigenbase. Any base of R square is an eigenbase and B doesn't. Okay. So here you are getting, but here you are not getting that the base, right? You can see that. Now, clearly I need to tell about that. Same, I already explained here. Correction. Right. We introduced that here very very brief about that. So I need to explain that geometric multiplicity of lambda is the dimension of the eigen space. In other words, a dimension of care A minus lambda I, right? And this geometric, and now algebraic multiplicity of lambda is the how many number of times it repeated, right? So number of times of lambda minus t occurs as a factor of A minus TID or lambda ID, right? Now, for example, if you consider this example, you got that this square of 0, 1, 0, 0 is one dimensional, geometric multiplicity is 1. Okay. Now, second example, that B you have taken, no, B. So, you got that geometric multiplicity is 2. Because here, you got that here 1. Here, you don't have. This you can observe. Okay, so both are having that the algebraic and geometric multiplicity is 2 only for I. This A matrix only it is applicable for A matrix. That's it forming of the base. It forms that the base, but does not the B. B we are not going to get that, only for applicable for A, right? So this is the difference between A to B now. So again, I'm repeating that here. So geometric algebraic multiplicity is the how many number of times lambda is repeated. But this is n minus a. Okay. So that we can say in other words a dimension of a minus lambda I. Okay. So that's the thing with that. Now nothing will be there in this topic. That's same as it is. So I'm not going to give that much more about that the theory part here, because already you know about that very in depth of this how to practice all the problems also. We know that, but I need to tell about that this topic also will be there in before going to that the advanced eigenvalues and eigenvectors. Okay, so these are all the three theorems also there. How to form that the eigen basis, no? So gi which is less than or equals to ai, and then we have that both will be there if ai equals to n, if and only if det of a minus pd if factors completely into the linear system. So we can see that. So hope I think everyone understood about that this very small topic of this today's